In September of 2022, NASA released an image that stopped scientists mid-sentence, not because it was beautiful, though it absolutely was, but because what appeared in that image was not supposed to be there, at least not like that, not that clearly, not with that level of detail from something sitting 4.5 billion kilometers away from us. What James Webb captured when it turned its golden mirror toward Neptune shattered assumptions that had been sitting untouched in planetary science textbooks for over 30 years. And the deeper scientists looked, the more unsettling it became. What we thought we knew about Neptune. Let's start where every good mystery starts, with what we thought we already knew. For most of human history, Neptune did not exist, not because it wasn't there. Obviously, it was there, doing its slow, freezing loop around the sun the whole time, completely unbothered by our ignorance, but we didn't even discover it until 1846. And the way we discovered it is one of the most remarkable stories in the history of science. Astronomers noticed that Uranus was wobbling. Not dramatically, not in a way you'd notice on a Tuesday afternoon, but mathematically, its orbit wasn't quite right. Something was pulling on it. Something big. Mathematicians Urbain Le Verrier and John Couch Adams independently calculated where that something had to be. They pointed a telescope at that spot in the sky, and there it was. Neptune, discovered by math before anyone ever actually saw it. For over a century after that, Neptune was essentially a smudge, a faint bluish dot that even the best ground-based telescopes could barely resolve into anything meaningful. We knew it was big, about 4 times the diameter of Earth. We knew it was far, roughly 30 times farther from the sun than we are. We knew it was cold, with temperatures plunging to around negative 214 degrees Celsius on the cloud tops, which, for context, is the kind of cold that makes Antarctica feel like a spa day. Then, in 1989, everything changed. Voyager 2, the only spacecraft ever to visit Neptune, flew past it on the 25th of August and sent back images that genuinely astonished the world. We saw a dynamic, turbulent planet. We saw the Great Dark Spot, a storm system roughly the size of Earth spinning in Neptune's southern hemisphere. We saw wispy white clouds streaking across brilliant blue atmospheric bands. We saw faint, thin rings. We saw a bizarre moon called Triton that appeared to have geysers shooting nitrogen gas into space. It was extraordinary. And then Voyager 2 kept going, disappearing into the outer solar system, and we were left with those images, those one brief flyby's worth of data, and not much else. For 30 years, that was essentially the sum total of what we knew about Neptune up close. The Hubble Space Telescope gave us some additional glimpses, enough to notice that the Great Dark Spot had disappeared by 1994, which raised immediate questions about how dynamic Neptune's atmosphere really was. But Hubble was never designed to look at something this faint, this far away, in this kind of detail. Neptune from Hubble looked like a blue marble with some vague features. Pretty, scientifically limited. So, when James Webb turned toward Neptune, scientists were cautiously optimistic. What they got was something else entirely. Why Neptune was almost impossible to see clearly. Before we get to what Webb actually saw, we need to talk about why seeing Neptune clearly is so extraordinarily difficult. Because I think people underestimate just how hard this problem is. Neptune sits at an average distance of about 4.5 billion kilometers from Earth. Light, the fastest thing in the universe, takes approximately 4 hours to travel from Neptune to us. That means when you look at Neptune, you are seeing it as it was 4 hours ago. Which is fine. Neptune moves slowly enough that 4 hours doesn't matter much, but the distance creates a different problem. The sun, at Neptune's distance, appears about 900 times fainter than it does from Earth. Neptune receives almost no sunlight. It is perpetually shrouded in a kind of dim twilight that we can barely imagine. This means that telescopes trying to image Neptune are working with almost no reflected light. They are trying to capture detail from an object that is barely illuminated billions of kilometers away through the distorting blur of Earth's own atmosphere if you're using a ground-based telescope. The other problem is size. Even though Neptune is 4 times wider than Earth, at its distance from us it appears incredibly tiny in the sky, about 2.3 arc seconds across for those keeping score at home. To put that in perspective, that's roughly the same apparent size as a golf ball viewed from about 1.5 kilometers away. Every telescope before Webb was fighting these combined limitations: distance faintness, apparent size, and atmospheric distortion. Some ground-based telescopes using adaptive optics technology that corrects for atmospheric blurring in real time managed to capture Neptune with reasonable clarity in recent years. But reasonable clarity still meant missing enormous amounts of detail. Webb was built to solve exactly these kinds of problems, but not in the way most people think. What James Webb actually is, here's the thing about James Webb that most people get wrong. They think of it as just a bigger, better Hubble, a more powerful version of the same basic idea. It is not. Webb and Hubble are fundamentally different instruments designed to see the universe in completely different ways. Hubble operates primarily in visible and ultraviolet light, the kind of light human eyes can detect. Webb operates primarily in infrared light, which is essentially heat radiation. This is not a minor technical distinction. It changes everything about what the telescope can see and how. Infrared light passes through dust and gas that blocks visible light. This is why Webb can peer inside stellar nurseries, looking through clouds of gas and dust to see stars being born, something Hubble simply cannot do. Infrared light from the most distant galaxies in the universe has been stretched by cosmic expansion until it shifts out of the visible range and into the infrared, which is why Webb can see farther back in time than Hubble ever could. And for Neptune specifically, infrared sensitivity matters enormously. Neptune's atmosphere is rich in methane. In visible light, methane absorbs red light and reflects blue, which is why Neptune appears that iconic deep blue color in Hubble images and in Voyager photographs. But in the infrared wavelengths that Webb uses, methane behaves very differently. It absorbs infrared light strongly. Areas of Neptune's atmosphere where methane is dense appear dark in Webb's images. Areas where methane is thin, or where other gases dominate, appear bright. This means Webb is not just seeing Neptune's surface appearance, it is seeing through the atmosphere to different depth levels, mapping chemical composition, tracing gas concentrations, revealing structure that is simply invisible to any telescope working in visible light. Then there is the matter of Webb's sheer collecting power. Its primary mirror is 6.5 meters across, composed of 18 hexagonal gold-coated beryllium segments that unfurled in space like some kind of impossibly expensive flower. Hubble's mirror is 2.4 meters. Webb's mirror collects about 6.3 times more light than Hubble, which in practical terms means it can see things dramatically fainter and in dramatically more detail. Webb also operates in space, far from Earth's atmospheric distortion, positioned at a point called the second Lagrange point, about 1.5 million kilometers from Earth, where it sits in a stable gravitational balance between Earth and the Sun. It is shielded from the Sun's heat and light by a tennis court-sized sun shield made of 5 layers of a material called Kapton, keeping the telescope itself cooled to around negative 233 degrees Celsius. It has to be that cold because infrared detectors are themselves sources of heat, and if the telescope were warm, its own warmth would blind its sensors. All of this engineering, every single design decision, was made in service of one goal: seeing things we have never been able to see before. When that mirror turned toward Neptune, everything was about to pay off. The moment the images came in, and the scientists went quiet. That is not a dramatic embellishment for the sake of this video. That is what actually happened in the rooms where people were first processing and viewing the Webb data from Neptune. Heidi Hammel, a planetary astronomer who has spent decades studying Neptune and who serves as Webb's interdisciplinary scientist for solar system observations, described seeing the images for the first time as something that made her catch her breath. And when you look at the images yourself, you understand why. And I know everyone says that about things on the internet. Bear with me here, because this is different. In Hubble images, Neptune is a mostly featureless blue disk, with some faint banding visible if you know where to look. The rings, which Voyager 2 detected in 1989, are completely invisible in Hubble imaging. They are simply too faint and too thin for Hubble to pick up against the glare of the planet itself. In the Webb images, Neptune is not even particularly blue. Remember what we said about methane absorbing infrared light. The planet appears in grays and whites with dark banding visible in its atmosphere, which we will get to shortly. But that is not what makes you catch your breath. What makes you catch your breath is the rings. In the Webb images, Neptune's ring system appears with a clarity that was previously unimaginable. Sharp, distinct, brilliant white arcs cutting across the darkness around the planet. Rings that had only been glimpsed as vague suggestions in 30-year-old Voyager data, suddenly visible in extraordinary detail, showing structure and brightness that nobody fully expected. Scientists knew the rings were there, but seeing them like this, after 33 years of knowing they existed but barely being able to confirm it, was genuinely emotional for people who had spent careers studying this planet. Heidi Hammel has called it one of the most joyful moments of her professional life. And given how things usually go in planetary science, where exciting means our instruments detected a possible anomaly that may warrant further investigation, that is saying something significant. But the rings were only the beginning of what Webb revealed, and this is where it starts getting genuinely strange. The rings nobody saw coming. Neptune's ring system is not like Saturn's. Let's just establish that immediately so nobody is picturing the wrong thing. Saturn's rings are vast, bright, and made primarily of ice, which reflects sunlight brilliantly and makes them easy to see. Neptune's rings are dark, thin, and made of material that absorbs light rather than reflecting it. They were entirely unknown until Voyager 2's flyby in 1989, 30 years after Saturn's rings had been studied in detail from Earth. That's how faint and dark they are. Neptune has 5 named rings. Working outward from the planet, they are Gal, Leverrier, Lassell, Arago, and Adams, all named after people involved in Neptune's discovery or early study. The outermost ring, Adams, is the most interesting. It contains 5 dense arcs, regions where the ring material is much more concentrated, which have been given names in a beautifully optimistic theme: courage, liberté, égalité 1, égalité 2, and fraternité. These arcs were known about before Webb. What was not understood was why they exist. Ring arcs should not be stable. In a normal ring system, gravitational interactions and orbital mechanics should spread the material evenly around the ring over relatively short timescales. Cosmically speaking, the fact that Neptune's ring arcs have persisted for at least 33 years from when Voyager 2 saw them to when Webb imaged them suggests something is actively confining them. The leading theory involves small moons called shepherd moons, which orbit near the rings and use their gravity to herd the ring material into arcs. Voyager 2 spotted a moon called Galatea orbiting just inside the Adams ring, which fits this model. But the math has never quite worked perfectly. Galatea alone does not fully explain the arc structure. What Webb's images revealed made this problem both more fascinating and more confusing. The ring arcs in the atom's ring were still there, still in roughly the positions expected based on their orbital motion since 1989. But their brightness and structure showed subtle differences from Voyager's data. Some arcs appeared slightly brighter than expected. The distribution of material within the arc showed features that the simple Shepherd moon model struggles to explain. This is the kind of discovery that makes planetary scientists simultaneously excited and frustrated. Excited because it means there is something real and unexplained to investigate. Frustrated because the something real and unexplained does not come with an instruction manual. But honestly, rings were not even the most surprising part of what Webb found around Neptune. For that, we need to talk about a moon that should not exist. The moons, and the one that shouldn't look like that Neptune, has 14 known moons. Most of them are small, dark, forgettable rocks tumbling through elongated orbits far from the planet. Captured objects, almost certainly. Ice balls that wandered too close billions of years ago and never left. Scientifically useful. Not exactly the kind of thing you bring up at a dinner party. And then there is Triton. And Triton is a problem. It is Neptune's largest moon, bigger than Pluto, and it orbits backwards. Every other substantial moon in the solar system orbits in the same direction its planet rotates. Triton goes the other way, like that one person at a concert who is absolutely defiantly not doing the wave. This is not a quirk. It is a screaming signal that Triton did not form here. It was captured, probably from the Kuiper Belt, in a violent gravitational ambush billions of years ago that almost certainly destroyed whatever moons Neptune originally had. And here's the part that should keep you up at night. That backwards orbit is slowly killing Triton. Tidal forces are gradually dragging it inward. In about 3.6 billion years, Neptune will tear it apart entirely. Mark your calendars. Now, here is what Webb revealed. In the infrared images, Triton is brighter than Neptune itself, a moon outshining its own planet. This is not an error. Triton's surface is coated in nitrogen and methane ices processed by cosmic radiation into organic compounds called tholins, making it one of the most reflective objects in the solar system. More importantly, Webb's spectroscopic analysis detected carbon dioxide ice on Triton's surface that no previous instrument had confirmed, a new chemical fingerprint, hiding in plain sight, waiting 30 years for a telescope powerful enough to read it. The atmospheric discoveries that rewrote the textbooks. The rings were unexpected. Triton's brightness was striking. But what Webb found in Neptune's atmosphere is the part of this story that is actively rewriting textbooks, not in the footnotes. In the main text, first, some quick context on what we were dealing with going in. Neptune is classified as an ice giant, which is one of science's more misleading labels. There is no ice floating around inside Neptune that you would recognize. The term refers to the interior composition, a hot, dense, supercritical soup of water, ammonia, and methane under pressure so extreme that our everyday concepts of solid, liquid, and gas basically stop applying. Above that sits an atmosphere of hydrogen and helium laced with methane. And above that, the cloud layers Webb was now staring directly into. Here is the mystery that has haunted planetary scientists for decades. Neptune radiates 2.6 times more energy than it receives from the sun. It gets 900 times less sunlight than Earth does, yet it generates the fastest winds in the entire solar system. Voyager 2 recorded wind speeds approaching 2,000 kilometers per hour at certain latitudes. 2,000. That is fast enough to cross the continental United States in about 8 minutes. Something deep inside Neptune is generating enormous amounts of energy, and nobody has definitively explained what. Webb did not solve that mystery, but it gave scientists their clearest look yet at the atmosphere those winds are driving. The infrared images revealed distinct banding across Neptune's atmosphere, dark lanes and bright regions corresponding to different chemical compositions at different depths. Webb was not just photographing the surface layer, it was seeing through multiple atmospheric levels simultaneously, something no previous telescope could do. And then there was the South Pole, a brilliant, unmistakable bright patch centered exactly at Neptune's south pole, surrounded by a darker collar just off the pole. Scientists had caught faint hints of this feature before using ground based adaptive optics. Webb made it undeniable. The leading explanation is a polar vortex driven by 40 straight years of continuous sunlight on the southern hemisphere. Neptune's year is 165 Earth years long. Each season lasts roughly 40 years. The South Pole has been in summer since the 1980s. The result is a concentrated circulation system 10 degrees warmer than the surrounding atmosphere. 10 degrees sounds trivial. On a planet averaging negative 200 degrees Celsius at the cloud tops, it is anything but. Webb also tracked individual bright cloud features evolving in real time, something that was simply not possible before, which matters enormously because Neptune's storms are strange. The great dark spot that Voyager 2 photographed in 1989 was the size of Earth. By 1994, Hubble found it completely gone. A planet-sized storm vanished in 5 years. Jupiter's Great Red Spot has been spinning for over 350 years. Neptune operates on a completely different clock, and Webb is finally letting us read it. The deeper implications, what Neptune is telling us about the universe. Here's the part most news coverage skipped entirely in favor of showing the pretty pictures. Which, fair. But stay with me, because this is actually the most important piece of the whole story. Neptune is not just interesting because it is far away and has weird rings and a backwards moon. Neptune is interesting because it is probably the most common type of planet in the galaxy. And until very recently, we could barely study our own example of one. Since the 1990s, astronomers have been cataloging planets around other stars. Early detection methods favored large planets close to their suns, which is why we initially found a lot of hot Jupiters, massive gas giants essentially slow cooking in tight orbits. But as the data accumulated, a pattern emerged that nobody quite expected. The most common planet type out there appears to be something between Earth and Neptune in size. Bigger than us, smaller than the gas giants. Scientists call them super-Earths and mini-Neptunes, and they are absolutely everywhere. Here is the uncomfortable part. Our solar system has none. We jump straight from Earth-sized to Neptune-sized with nothing in between. That gap is either a coincidence or a deeply important clue about how our solar system formed differently from most others. This means Neptune is our only nearby model for the most abundant category of planet in the Milky Way. Every atmospheric measurement Webb takes, every chemical signature it detects, every storm system it tracks, directly feeds the models scientists use to interpret exoplanet observations. Webb studying Neptune is Webb studying billions of other worlds simultaneously. And there is one more layer. Neptune was not always where it is. Models suggest it formed closer to the sun and migrated outward, a journey that triggered a period of catastrophic bombardment of the inner solar system around 4 billion years ago, an event that helped shape the early Earth. Neptune is not just a distant ice giant, it is a record of our own origins, and Webb is finally giving us the tools to read it. What we still don't know here is the part where I am obligated to be honest with you, and where the story gets genuinely uncomfortable. Webb's Neptune images are extraordinary. They are the clearest, most detailed observations of Neptune ever made. They have revealed ring structure we could not see before, atmospheric features we could not map before, surface chemistry of Triton we could not characterize before. They have already changed our understanding of this planet in meaningful ways. And they have also raised questions that nobody currently knows how to answer. The internal heat source driving Neptune's extreme winds remains unexplained. The fact that Neptune radiates 2.6 times more energy than it receives from the Sun is one of the oldest unsolved problems in planetary science. Jupiter and Saturn also radiate excess heat, generally attributed to ongoing gravitational contraction, the planets slowly shrinking under their own gravity and converting that into heat. But Neptune and Uranus are different. Uranus barely radiates excess heat at all, while Neptune radiates a lot. Two planets of similar size and composition behave completely differently in this regard, and nobody has a fully satisfying explanation. Webb can measure Neptune's heat output more precisely than ever before. What it cannot do is see inside the planet to determine what is generating that heat. The interior remains inaccessible. We are still essentially inferring what is happening kilometers below what we can observe. The ring arcs, those persistent clumps in the atom's ring, are still not fully explained. The Shepherd moon model is insufficient. Something is confining those arcs, something we have not fully identified or characterized. And Triton, the backwards moon, with its decaying orbit and its geysers and its weird icy chemistry, raises a question that Webb's observations have sharpened rather than resolved. What exactly is the long-term fate of the material Triton is slowly losing to space? Webb has given us better data on this process without yet giving us complete answers. This is how real science works, and it is worth saying that clearly. Each discovery opens 3 more doors, answers one question and generates 4 new ones, and leaves researchers simultaneously more knowledgeable and more aware of how much they do not yet know. Webb's Neptune observations are a perfect example of this. Richer, more complex, more mysterious than before. So where does this leave us? In September of 2022, a telescope parked 1.5 million kilometers from Earth turned its gold-coated mirror toward the outermost planet and sent back images that made scientists catch their breath. Rings that had been invisible for 33 years appeared in brilliant clarity. A polar vortex revealed itself in unmistakable detail. A backwards moon outshone its own planet. Atmospheric structure invisible to every previous telescope suddenly appeared in the infrared, layered and complex and dynamic. This is not a story about pretty pictures, though the pictures are genuinely extraordinary. This is a story about what happens when you finally build an instrument capable of seeing something you have been trying to understand for over a century and a half. Neptune has been known to us since 1846. 176 years of knowing it was there, knowing roughly what it was, and being almost completely unable to see it clearly. One spacecraft flyby lasting a matter of hours in 1989, giving us our first real look, 30 years of Hubble observations that were honest in their limitations. And then Webb. What the James Webb Space Telescope did for Neptune is what good science always does at its best moments. It took something we thought we understood and showed us how much more complicated and interesting the reality was. Neptune is not a simple blue ball of frozen gas at the edge of our solar system. It is a dynamic, complex, chemically rich world with rings that contain unexplained structures, a captured Kuiper belt object for a moon that is slowly being consumed by tidal forces, atmospheric systems we are only now beginning to map in 3 dimensions, and an internal heat source we still cannot fully explain. The fact that worlds like Neptune appear to be the most common type of planet in the galaxy makes all of this doubly important. When we figure out Neptune, and Webb is giving us the tools to finally start doing that, we are not just learning about one cold world 4.5 billion kilometers from home. We are building the framework for understanding billions of worlds we will probably never be able to visit. Neptune has been sitting out there in the dark, incredibly far away, for 4.5 billion years, just doing its thing, circling the sun once every 165 years, driving its incomprehensible winds, holding on to its backwards moon, maintaining its mysterious rings, being the most common type of planet in the universe in almost total obscurity. It waited 176 years for us to discover it. It waited another 33 years for us to build something capable of really seeing it. The images are in, the data is being processed. The questions are multiplying faster than the answers, and James Webb is just getting started.